This conference will now be recorded.
Hello everyone, hope you are doing great. I received your comments. I hope that we can deal with each other in the best way, in the most efficient way. Today I tried one class that just only one student was attending. So I recorded the video, but I found there are some matters that have to be fixed. So, and actually the length of the video was very long. So I was afraid that some of you be a bit bored along the video. So I am trying now to shorten the video and explain a bit not faster, make it in an organized way that when you are watching the video, you can actually, when I ask you to pause, search the information and continue. So hopefully the method works. I wait for your comments. If you have any, please. Sure, your idea, your suggestion, your comments are very important to all of us and to me. So if you remember, we already studied about open and closed system last week. I already uploaded the material for you on the Moodle that you can refer. But I tried to summarize the study material of last week, of the last month and this one, or last week and this week, in a way that you can just remember what we have studied so far. So these things we already studied, but I plan to make it in a summary way that you can recall what we have studied. First, I explained to you what is a system, what is a surrounding, and I'm sure you already remember all of these things. And then I explained to you what is a closed system and what is an open system. As you may remember, in a closed system, we mentioned that mass is not going to be transferred through the system boundary, but energy may transfer. In an open system, both mass and energy will pass through the system boundary. So if you remember, we mentioned in an open system, you are facing with the mass rate, and while in a closed system, you are facing with the fixed amount of the mass, that we call it M for closed system about the mass, and M dot or mass rate for open system. And after that, I told you a system can have three types of energy, or can possess three types of energy. That was kinetic energy, potential energy, and internal energy. Kinetic energy, I explained to you, you can calculate these terms by considering the amount of the mass and velocity of the system. Potential energy is an energy related to the position of the system in a gravitational field, means Earth. So you can just have the amount of the, you can calculate potential energy by referring about the mass, acceleration, and about the gravitational acceleration and the position of the system. So, and the final value was internal energy, that I told you any types of energy that is not in the category of kinetic and potential energy and related to translation, rotation, vibration, electrochemical interaction of the molecules, atom, and subatomic particles inside the system relate to this category. And I discussed with you all these terms are similar for open system. The only difference is, as long as it considers the mass rate, you can measure the energy rate instead of energy and instead of energy. And after that, I explained to you these three types of the energy that the system can have can only be transferred through two ways: heat and work. And we explain and actually work on the terms of heat, terms of work. I explained to you if a system receive the actually heat is positive, if the system lose the heat is negative, if the system do the work on the environment is positive, and if the system receive the work from the environment is negative. So And based on that, we define the first law of thermodynamics that is known for energy balance as well in closed system. And as you remember, I defined you the same equation for the open system, just you have to consider the energy rate instead of energy. This actually formula of energy balance can be converted to these forms of energy balance that in this equation we have delta U and W, and in this equation, by changing delta U to delta H and actually reforming the equation, we should have work of the shaft. If you are interested later, I can tell you how you can change these two formula together to each other, but they are both same. So the only difference is that as you put delta H, the work of the system is just work of the shaft. Actually, the system has work of flow as well, but that one in the modification of the equation has been crossed. So just be sure, based on the input data or based on your intention, what formula you want to decide to use for open system, either of these or that one. So this is just a summary. And another term that I want you to get to know about that is a specific property. A specific property is any property like volume, like enthalpy, like entropy, like internal energy, if they are divided by the mass. Maybe sometimes you see in some books they are divided by the mole, but in your book you are usually facing a specific property, dividing that property by mass or mass rate. So for example, if you want to have the specific volume, you should know the volume that is divided by mass, or volumetric flow rate divided by mass flow rate. So it should be the same. If in closed system, the term is actually the exact value, but in the open system, actually it is in open and closed system. In open system, it is rate. In closed system, it is that value absolute. So that is another definition for a specific value. So if you have a specific value, if you multiply it by the mass or mass rate, you can calculate that value or flow rate of that value. So that is just a definition I want you to know, because you need this one. So that one is the very, very abstract of your study so far for open and closed system, that based on that you can solve most of the problem in this chapter. So I think this one I already solved for you, but I just give it a try now. Please, if you need any time to read, pause the video, think about the question, and then try to check about the solution that I refer to you here. So here you see air at 300 Celsius and 130 kilopascal, flow through a horizontal ID, a 7 centimeter ID pipe at the velocity of 42 meters per second. So they asked you to calculate kinetic energy by assuming the gas is ideal in the beginning. So and then it asks you to consider the changes of kinetic energy if the outlet temperature is 400, and at the last it asks you about another part of the question. So first we want to calculate the EK in the inlet. Before you go to solution, please pause the video and think about the solution before you go through the answer. This answer I already put for you on the module, so you can refer to the answer. So as I draw the diagram for you, air enters in 7 centimeter ID of pipe by these actually properties. Temperature is 300, pressure is 130 kilopascal, velocity is 42. This one actually I calculate for you, the area just to have the area of the pipe. So we are asked for EK, or potential, kinetic energy in the inlet. So as I mentioned to you before, when you are asked for a element, first check if you have any direct formula to measure that element or not. So in that case, we have EK equal to half of mass rate multiplied by velocity power 2. Okay, for solving this equation, we have already V1. So the only terms we don't have is mass flow. So first we have to calculate the mass flow. And we already discussed about some formula that you are able to calculate the mass flow rate. So if you have density, is okay, you can calculate the mass flow rate because A and velocity you already know. So how we can calculate the density of the gas? That is a formula that we discussed in the class. PMW RT. MW is the molecular weight of the air that you should, they will give it to you. It's not something that you should memorize. P is the pressure, R is the gas constant, and T is the temperature of the gas at Kelvin. So by merging these two equations, we will reach to this general equation. Mass rate equal to PMW RT multiplied by area multiplied by velocity. I just substitute the all values that we have in this equation. P is the postcode. Whatever we have to change based on the unit, we will fix. Here is the molecular weight of the air. Here is the gas constant. This one is the temperature of the gas in the inlet. That one is the velocity, and that one is the area that I calculated here. So by that one, we can calculate the mass flow rate. That in the beginning it was based on gram per second, then I converted to kilogram per second. Now by knowing the M, you can easily calculate the EK, kinetic energy. So please try yourself as well to go through the same process and see if you have any problem. Please let me know if you have any problem. So that is the first part of the question. The second part asks you to calculate the delta EK, or changes of kinetic energy, if the air leaves the pipe at 400 Celsius at constant pressure. So first of all, to calculate delta EK, this is a formula we already know. So in this formula, you already know m dot mass flow rate. You know V1, velocity in the inlet, but you don't know velocity in the outlet. So what we need to calculate this, we need to know V2. So how we can calculate V2? There are different ways, but I tell you the easiest way. We know the mass flow rate in the inlet and outlet is the same. So we just write the same formula I show you here, mass flow rate for the inlet and outlet. So we just put the inlet and outlet for each of them. We know they are equal. So we know P is similar, MW is similar, R is similar, T1 and T2 are different, area is same, V1 and V2 we don't have. So from this balance, mass balance, we can reach to the point that how much is V2. So I think it's clear. So as long as we know V2, we can calculate delta EK because all the other parameters are known. The last part of the equation, the last part of the question asks you why we cannot say, let me read the question. Let me share with you the question. So in the last part of the question, they ask you why it would be incorrect to say the rate of transfer of heat to the gas in part B is equal to rate of change of kinetic energy. It's saying that why is wrong to say Q is equal to delta EK. Am I right? Okay, why it is wrong, right? So we have to give the information why this one is wrong. So we come back here. We know this equation from mass energy balance for closed system, right? Here we know delta EK we already calculated. Delta EP is 0 because there is no changes of the height of the system of the pipe. Delta U is not 0 because the temperature is changing. So we cannot say delta U is 0, but there is no work inside the system. So as you see, Q is equal to changes of kinetic energy and delta U. You have to put a dot here because they're all right. So that is wrong if we say Q is just equal to delta EK because delta U is another term that is affecting the situation here. That is the final answer of this question. Please pause the video now and try to solve the problem one more time. I want to be sure that you all understand this question. So now I continue with the rest of the lecture. So another example I put for you here is about a gas turbine. 500 kilogram per hour of steam drives the turbine. The steam enters the turbine at 44 atmosphere and 450 centigrade at a linear velocity of 60 meters per second. So these are the information of the inlet of the steam that enters the turbine and leaves at a 0.5 meter below the turbine inlet at atmospheric pressure. So we know there is some changes of the height. We know that the outlet pressure is atmospheric, means 1 atmosphere pressure, and velocity is 360. The turbine delivers shaft work at a rate of 70 kilowatt. So here it mentioned the work is exactly shaft work. So in this situation, you always use the second formula for open system for energy balance because you have the shaft work. And the heat loss from the turbine is estimated to be 10 kilocalorie per hour. Because this heat was lost from the system, so you have to consider negative. Because this work has been done by the system, it is positive. That is the only thing you have to know. Calculate the specific enthalpy change associated with the process. So first of all, it asks you for enthalpy. So that is another reason we have to use the second formula for energy balance of open system. And finally, it asks you for a specific enthalpy. You remember, a specific enthalpy means enthalpy divided by mass, or enthalpy rate divided by mass rate. So if we calculate, if we finalize, we get the idea of how much is the changes of enthalpy, then we can divide it by mass flow rate, then we can be clear how much is the specific enthalpy. So how we start? We start with drawing the diagram of this process first, right? Even you can try to draw it first, and then we continue. You pause the video whenever you feel you have to. So we come here. So we have a turbine. There is inlet steam to this turbine that is 500 kilogram per hour. Pressure is 44. Temperature is 450. Velocity is given to you. It mentioned that is there is 5 meter lower height for the outlet. It mentioned the pressure is atmospheric and velocity is given to you. What else they give it to us? Work of the shaft, that is clearly 70 kilowatt. It is from the problem. They give you the heat loss. As long as the heat was lost, it is negative amount. So they ask us a specific. This symbol is for a specific enthalpy changes. So what I did, so we know already what we want. We need delta H. The only way we can calculate delta H is through the energy balance for open system. I select the second formula. I explain for you why. So that is the one. Here we have to calculate delta EK. We can calculate why, because we have V1, we have V2. Delta EP we can calculate because we have the changes of the height inside the system. Delta H we need, Q is given to you, WS is given to you. So to calculate the changes of enthalpy, we can just calculate this one minus this one, and this one. I just rearrange the formula for you. Here I just change the unit of the mass flow rate. It was 500 kilogram per hour. I changed it to kilogram per second. I changed just the conversion factor for the hour to second. So here we know we have to start to calculate each term, then we can calculate delta H. Agree? First we start with the Q. And one more thing, to be able to add or reduce these amounts, all of these energy rates should have the same unit. If not, you cannot add them together or deduct from each other. So we start with the same unit. Here I selected the unit be kilojoule per second because I want to be all of them the same unit, unified. So I want to change kilocalorie per hour to kilojoule per second. Here is just changes of the unit. Kilocalorie, you have to refer to the conversion factor in the book that you have. I show you the picture of the book, and all of you have the book already, the hard copy of the book, all of you have. So that is the kilocalorie to joule, the unit, and then we change joule per kilojoule, and here we have to change hour to seconds. So that is the last value for changes of for the heat loss. For the shaft work, they already clearly they give it to you. It is 70 kilowatt. Kilowatt means kilojoule per second. You already know the term watt means joule per second, and kilowatt means kilojoule per second. So that value is given to you directly. You don't need any conversion. The third value is calculation of changes of kinetic energy. We already know how we can calculate the kinetic energy changes, right? So through this, we already have all the data in it. We have mass rate, mass flow rate. We have velocity in the outlet, velocity of the inlet. So we can just substitute. We can just substitute. That is the final value. Because again, we want kilojoule per second. I just change kilojoule, joule to kilojoule. That's it. So I have this one. Now we go to delta EP. Again, you know the formula is m dot G delta Z. Just we substitute m dot G and delta Z. As long as the height drop, we know delta Z is negative. So it is negative delta Z, and we just substitute it. It is joule per second. Again, we just convert it to kilojoule per second. So now everything is done. You already have Q, you have WS, you have delta EK, you have delta EP, and all of them have the same unit. So you can add them together in this formula. So that is the final value. But we know this one is energy rate. The problem asks us a specific enthalpy change. What is a specific enthalpy? As I mentioned, the changes of enthalpy rate divided by mass flow rate. We have this value. We know what is the mass flow rate. So it is kilojoule per kilogram. So that's what is a specific enthalpy. So hope this one is clear for you. Again, please pause the video and check if you can solve it on your own. Then you go ahead with the rest of the video, because I want to make the video length short, so you can pause the video anytime, try to solve, try to do it by yourself. If you have any problem, please don't hesitate to write to me. I will try to make further explanation if you need. So we continue now with the rest of the course. So that example we already solved. So how you want to use a steam table? As an engineer, you know there are so many applications of water and steam in the industrial plant. So we don't need to calculate the properties of water if we need, actually, if we are using this substance in industrial plant, or even for some other component, a specification is already calculated and tabulated for you in the table. But here we specifically refer to the water. First of all, you know what is a state property and how you can calculate, because the state property are the properties that they are dependent only on the state of the system, right? It doesn't matter how the system reach to that state. You just consider that exact state of the system. So for example, for enthalpy, for example, if there was a changes of the system, like temperature, pressure, composition of the system change from this state to another state. For calculating the enthalpy, you just have to refer to the state of the system in these two movements. For these types of property, you can use the exact values. Depends on the temperature and pressure of the system on that state. So that is why we are able to use information of a specific volume, a specific enthalpy, and a specific internal energy from the tables. Just to recall, you studied about already the phase diagram of the water. If you see through this phase diagram, the water state relates to temperature and pressure. Here actually is the triple point. In this triple point, water exists actually coexists in three phases at the same time. As far as I know, we don't have this situation on the Earth, but based on I think the research suggests that this situation happens in Mars, that the water coexists in three different phases at the same time. But it's okay, leave it. This saturated line is very important for you. In this saturated line, water actually water and the vapor are in the saturation and equilibrium to each other, right? So for water to be saturated steam or saturated liquid, for being saturated liquid, in any temperature, there is a specific pressure. In this situation, any specific temperature, it should be a specific pressure for water to be saturated. So if you know the temperature, somehow from the table, you can see what is the pressure if the water want to be in the saturation. Below this line, we have superheated steam, and above this, there is subcooled liquid that you may work with them. So for this saturated steam and saturated liquid and superheated steam, you can refer to three tables at the end of your book. Even I put these three tables for you in the module that you can easily refer. So in the steam table, you can find saturated steam by using only temperature or pressure. Because if you have temperature, you can see how much is pressure. And if you have pressure, you know how much is temperature. And for superheated steam, but in superheated steam, you should know exactly, because you know there are so many regions that is superheated. You should know the temperature and pressure for any specific point, okay? So in this table, based on this input information that you have, you can find a specific enthalpy, a specific internal energy, and a specific volume for water or steam or superheated steam. Water, saturated steam, and superheated steam. So if you look at the table you have, I want you use this table as I am solving the problem, because I want you refer to the table and find the value by yourself. So you have to, if you are given the water in saturation, you can refer to table B5 and B6. These two tables, as I can show you here, these tables I already give you. Table B5 is just properties of saturated steam based on temperature. So you know, for each temperature there is a specific pressure for water to be saturated steam, right? So that is B5 and B5. So you have until 102 Celsius. They already tabulated for you a specific volume, a specific internal energy, and a specific enthalpy. And you can see if you are referring to water or you are referring to steam, you have to consider which phase water exists in the problem that they are giving to you. Table B6 is, again, it is property of saturated steam, but they organize it based on the pressure. And actually the range of temperature and pressure inside this table is longer, is actually more wider. So you have information up to 221 bar and 374.15 Celsius. These information are for saturated steam. So if you are given the water in saturated steam phase, you can refer to either of these two tables. But if the information of water is given to you in superheated phase, you should refer to B7. In this table, as I mentioned, you should both know pressure and temperature. By only one point, you cannot find the information. So if you look at here, for example, at 10 bar and 200 Celsius of temperature, these are the specification of saturated steam, which is H in the first, a specific enthalpy, a specific internal energy, and a specific volume. So you can refer to both these two input data and find out what is the specific property you want. So hopefully you understand and you can practice. If you have any problem, again, you can just get online with me. I will show you. But you have to, I already sent you the soft copy of this table, and in your book, the last pages of the book, you have the hard copy of this table. So you can refer to that table as well. So this is a very brief explanation of how to use the information. So we give you one example here to just practice with you how to read the tabulated data from the steam tables. So please read the question first, pause it, and go to your steam table and try to find it before you read the answer. Here they ask you determine the vapor pressure, a specific internal energy, and a specific enthalpy of saturated steam at 133.5. So first of all, you consider what is the phase of the water. It is saturated steam. So by saturated steam, you have to use table B5 or B6, because B7 is just for superheated steam. So we consider, and we know either temperature or pressure. Here they give us temperature, 133.5. So you can just pause the video now and refer to the table to find it. But I will show you here just for your own understanding. So you remember we need 133.5. So you can use B5 or B6. That is B5. Temperature is 133.5. So what is the pressure here? All this information you may use. At 133.5, for water to be saturated, the steam pressure should be 3 bars. What is the volumetric, a specific volume? That is the specific. What is the specific? You have to read for steam, right? Because it is saturated steam. What is the specific internal energy for steam? It is the specific internal energy for steam. What is the specific enthalpy? That is the specific enthalpy. So you just practice how to read it. Now we go back to second question. That is the only, all of them are specific. That is why all are divided by kg. Determine the specific internal energy, a specific enthalpy of superheated steam at 10 bar and 370. So as long as it is superheated, you have to use table B7. And for using superheated steam, you should have both temperature and pressure, right? So we go back to the table. You just pause it and practice, please. Sorry. So we have to refer to superheated. So it is B7. B7, you already given what information they already give to you? 10 bar, 370. So we have to find first 10 bar. Yes, this is 10 bar and 370. That is 350. Next page. They didn't give us for 370, but we have information of 10 bar 400 and 10 bar 350. So what we should do, we should read, because we have to interpolate. If you are asked for a point that is not inside the table, but it is between the two other table, we have to interpolate. Interpolation, I wonder if you read about this or not. So now, for example, we already have the information at 400. This is for internal energy, specific internal energy. So you have at 400, how much is the specific internal energy you read from the table? At 350, how much is the specific internal energy? You just jot down. At 370, that is between these two lines, we want to calculate how much is the specific internal energy. You remember, actually, these all values are linearly actually related. So you consider you have one line and 3 points. So we use the slope. The slope of the line is constant, right? It doesn't matter. These 2 points, all these 2 points. A slope of the line is clear. So what we do, we first write the slope equation for this and this point. Means y2 minus y1, x2 minus x1. Now it is equal. This is the same slope, the same line, right? Now write the slope for these 2 points. Y minus y1, x minus x1. So as you have this information for any point, you can do interpolation. So I just read the information of all this one and put it here, and then we calculate. So just try to do this one for all the points. So hopefully you got the idea. So now we try to solve the first problem by using a steam table. So what is given to you? Liquid water is fed to a boiler at 24 Celsius and 10 bar, and is converted at constant pressure to saturated steam. For using energy balance regarding to the any types of components, you always have to consider the phase of the system rather than the temperature, pressure, and other information of the system. So we will see here how it affects, right? If you remember, in table, a steam table, we have both value for water and steam. So it's important to know in what state the water is. So it is liquid. It is liquid water that enters the boiler at this temperature and pressure and will be converted to saturated steam at constant pressure. So pressure is 10 bar. Calculate the heat required to produce 15,000 meter cube per hour of steam at existing condition. Assume that kinetic energy of entering liquid is negligible and that steam is discharged through a 15 centimeter ID pipe. So what it means here, kinetic energy of the entering liquid is negligible. So it means here there is no kinetic energy, or you can say there is no velocity, okay? But as it's discharged through the outlet, it comes within this ID of the pipe. So it comes with the velocity. So how we start usually? We start with energy balance formula. So this is the boiler. Liquid water enters in this condition. Temperature is given, pressure is given. It mentioned kinetic energy is negligible, so we can assume there is no velocity. It mentioned it will be saturated at the outlet. Pressure is given constant pressure, so it is the same pressure you have in the inlet. Volumetric flow rate is given to you 15,000 meter cube per hour. So I just do a conversion here, convert meter cube per hour to meter cube per second. So it is just a conversion, nothing else. ID of the pipe in the outlet is given to you 15 centimeter. That I just convert ID to the radius by considering meter to make the calculation is easier. So we need to know how much is the Q. To calculate the Q, we have to write the energy balance, right? Okay. As we go through this, we have to simplify first. If we don't have any of this term, we have to remove it. So we don't have any changes of the position of the boiler in the inlet and outlet. So there is no delta EP. There is no shaft work inside the boiler. So WS is 0 as well. So what will be left? Delta EK, kinetic energy changes, changes of the enthalpy, and finally Q. We need Q, so we have to understand what is these two factors. I just write them. That is the formula for calculation of delta EK, and this is a formula for calculation of delta H. So to be able to solve this, we need mass flow rate, we need V2, V1 is 0 because we already considered the kinetic energy in the inlet is negligible. And then we need H2, we need H1. So we start because before, without having these terms, we cannot calculate the Q. So we start by each term one by one. First, we go to rho mass flow rate. Because we have here, we have volumetric flow rate at the outlet. By this one, we can calculate mass flow rate. So I use the information of the outlet, right? But we know mass inlet is equal to mass in is equal to mass out. So as you calculate this mass, you can use it for all the equation. But as long as you are using this information, so you have to be sure you are using all the information in one side, not from this side and this side together. So I use the information of this side to calculate mass flow. For mass flow rate, it is one of the equation we know. Density multiplied by volumetric flow rate. Volumetric flow rate is given to us, but density we don't have. But what information we may have from the table, because it is a saturated steam. Density unit is kilogram per meter cube. What is a specific volume? A specific volume is meter cube per kg. So it is reverse form of the density. As long as you have a specific volume, you can calculate density. It is a constant formula because in the steam table they give you a specific volume. From that specific volume, you by default assume that you can calculate density, okay, through this formula. So because it is saturated steam, we have to use B5 or B6. We have to, the pressure is 10 bar, so we read volume, specific volume in the B5. B6, I want you pause the video and find a specific volume at 10 bar. We just put it in this formula, and in this formula to calculate mass flow rate. So this is a mass flow rate that you can calculate from this equation. Next one that we want to calculate is velocity in the outlet, right? To calculate the velocity in the outlet is easy, right? You already know the area because you know already the ID, you know the velocity. So, sorry, you know the volumetric flow rate. So by dividing volumetric flow rate by the area, we can calculate the velocity. So velocity is clear as well. So now we need H2 and H1. As long as we are dealing with water, we can use the steam table and read these values. So how we read these values? First, H2. We know the problem told us the water exits the boiler in saturated steam. As long as it is saturated steam and you have the pressure, you can read the specific enthalpy from the table, from table B6. Just check it out. Pause the video and check it out. That was the value we read from the table. But this one is in terms of specific. So it is divided by kilogram. So you have to multiply it by mass flow rate to get the energy rate. I'm sorry, I made a mistake here. I forgot to put the second here. Just to be sure, I am fixing this one. It should be second here, right? All of them. Here it should be, because I already multiplied by mass flow rate. Please fix this one, right? It should be second. I forgot to put the second. So here, as you multiply a specific enthalpy by mass flow rate, you will get kilojoule per second. Again, you can consider all of them be kilojoule per second or joule per second. I converted to joule per second, but up to you. The same thing we do for H1. H1 is liquid water. For water, you assume it is independent of pressure. Consider temperature to read the liquid water in table B5. For water, you read the specific enthalpy at 24 Celsius. That is a value you can read from the table B5. Again, because it is a specific value, you have to multiply by mass flow rate to make it energy rate. Okay? So you already fixed this value. So now we have all of the components. We have H1, we have H2, we have V, we have all of these components V1, we already got them, right? So now you can easily calculate. You can easily calculate Q. Again, I have to put 1 per second here. I'm sorry. In my calculation, I forgot. I don't know why. So this is how, from the simple energy balance equation, we can calculate any of the values that we don't have by considering the values that we have. So, and as long as you have a water, You can easily read the properties of water from the table, steam table that you have at the end of your book, and I put for you B5, B6, and B7. Hopefully it's clear for you. Okay, the rest I will leave it for now. So these were some examples. I just wanted to show how to use a steam table to solve the problem. Tomorrow I will continue with the rest of this session, hopefully by today, for 2 components, but it is the same theory, everything is same. Just you have to learn how to use a steam table, forget the properties of water in different phases, right? I hope it is clear for you. Please, when you are solving the problem, pause the video and be sure you are finding the data from the tables. If you have any question, please let me know. And I will try. I already discussed with Mr. Khalfan. I hope all of you discuss together and find it out how we want to arrange the quiz. Hopefully we can arrange a time. Let me know all your opinion. Have a nice day. Bye.